My name is Xiaoyang Bai, and I'm currently a postdoc fellow in the University of Hong Kong. I'm here to present this paper, Enhanced Velocity Field Modeling for Gaussian Video Reconstruction, which is a joint work between Hong Kong U and Zhejiang University. So the motivation of this paper is that current AR/VR display relies on stable, view-consistent virtual overlays in dynamic real-world scenes. But even today's latest AR/VR devices have the issues which include virtual object drifting and incorrect occlusion. This issue becomes more prominent for dynamic objects which we are trying to tackle here. So the core technical point to improve the display quality is that we must recover accurate geometry and accurate motion so that AR/VR rendering remains temporally consistent and visually convincing. Our work tackles this problem from both the motion and the geometry perspectives. For the motion part, we observe that existing dynamic Gaussian splatting works create very chaotic velocity fields, as seen in the left. And also, if we visualize the trajectory of each Gaussian, we can see that their trajectories are also very unstable and not very meaningful, as visualizing the lower right corner. So as a result, the whole frame is very blurry and unrealistic. The issue of geometry is the lack of Gaussians, especially when an object moves from a faraway place in the scene to a more closer to the camera. So you can see over here that as the people move towards the scene, their structure and their texture breaks because there's simply not enough Gaussian to represent them. Oops. So our approach addresses the aforementioned issues from both aspects. We use velocity rendering to solve the motion problem, and we apply flow-assisted adaptive densification, or in short, FAD, to address the lack of Gaussian problem. We observe that we have a significant improvement over existing baselines in the random motion area, and we also have a more reasonable prediction of Gaussian trajectory. So here is our pipeline, and I'm going to go through it very quickly. So firstly, as previous 3DGS and 4DGS works, we initialize the Gaussians using CoMap generated point clouds, and we select the first frame for constructing the initial point cloud. And then we assign each Gaussian a two-dimensional velocity attribute to control the movement of Gaussians. And these attributes are rendered using Gaussian rasterization to obtain a two-dimensional velocity field. So this process is actually similar to the differential rasterization in Gaussian splatting and volume rendering in NERF. So the basic idea is to blend the motion attributes of each Gaussian along the viewing direction, and we can subsequently supervise it by the pseudo ground truth generated by optical flow estimation algorithms. The other, so for losses, we design two losses to supervise the rendered motion. So the first loss is to calculate the consistency of Gaussian colors between neighboring frames. Basically, we warp the Gaussian color using predicted rasterized Gaussian motion, and we compare it to the ground truth color of neighboring frames to ensure that the colors stay consistent between two frames. And secondly, as we mentioned before, we directly supervise rasterized or rendered velocity using predicted optical field from existing algorithms to ensure that the trajectory of each Gaussian is constrained and is meaningful. Okay. So the next contribution of our work is the flow-assisted densification. So basically, we find that velocity rendering cannot solve the issue where Gaussians are simply missing in regions where it's like changing from shifting from a very far place to a nearby place. So to mitigate this issue, we introduce a densification strategy that adds Gaussian in challenging dynamic regions of the 2D frame, instead of like in addition to the original cloning and splitting densification strategy in 3D GS. So how this works is that we determine the position of the Gaussian that needs to be added according to the flow-based loss map, which is calculated in the first previous steps. And then we use the render depth to project it back to the 3D canonical space. And then we use spatial interpolation to generate the features of the newly added Gaussians. And finally, we complete the shallow array in dynamic regions in 3D. So we please refer to the paper for more details about this densification strategy. And finally, we also explore the possibility of leveraging the extended Kalman filter, or EKF, as a post-processing step to further refine the velocity of Gaussians. EKF is originally designed to refine and to smoothen the trajectory of, for example, moving vehicles, given a set of ground truth observations. So in our case, we use the pre-trained optical flow prediction as the ground truth observation, and we use the rendered Gaussian position as the estimated data, and we apply the EKF algorithm to smoothen the Gaussian trajectory and to align it better with the optical flow prediction. Our study demonstrates that this strategy effectively smoothens Gaussian trajectories and align them more closely with the optical flow result. And we claim that it is potentially useful, and it is possible to devise a multi-stage learning framework in dynamic JS for future works. So here are some visualization of our that we do. So on the left, you can see that our for example, velocity flow loss actually targets the region where motion is more prominent. In this case, the region around the human bodies. And on the right, you can see that our method can better capture the trajectory of each Gaussian compared to the baseline that's visualized a few slides ago. So here's a video of how the Gaussian trajectories look like. And here are basically some results from data sets including Neuro 3D and the NVIDIA. So you can see in the square area that our method can typically produce clearer and nicer dynamics across different scenes. And well, here are just more results that we want to show to you. So you can see that our method not only improves the visual quality in terms of RGB rendered images, but also the rendered velocity frames visualized in false color here. We compare our method against existing dynamic Gaussian splatting baselines like 4DGS, MotionGS, and SCGS. And more results can be viewed in our paper. and the supplementary material. So coming back to our whole pipeline, and here are some summarization of what we're doing. So we propose a pipeline called Flow Gaussian VR that is a dynamic Gaussian splatting framework that pays explicit attention to Gaussian velocity and Gaussian trajectories. We design flow-assisted adaptive densification to solve the lack of Gaussian problem. And we observe logic gains in render dynamic areas across different scenes. And we also explore the usage of extended common filter, we name it TVR, to further improve the smoothness and the consistency of Gaussian trajectory after the training has been done. A few limitations of our works include that the EKF application is still in its infant stage. It doesn't directly improve the quality of rendered RGB images in terms of metrics such as PS03. We still need to deal with the scale invariant situation of Gaussian, and that all of our improvements increases the training time of the dynamic GS, so moves us actually further away from the real-time dynamic scene reconstruction. And finally, we want to advertise the SQL of Asia 2025, which will be held in Hong Kong this December. So we welcome all of you to come and attend the conference. And thank you.
Thank you very much. There are some questions? Yeah.
Hey, thank you for the nice talk. I'm Shohei Mori from University of Stuttgart. I have a question about the adaptive, how's it called? Adaptive
densification.
Yeah, densification. When do you perform that? Every frame, or like a certain keyframes, or at the beginning or in the end?
Yeah, very nice question. So typically densification or density control or resampling, whatever, in Gaussian splatting is applied every a certain number of iterations. So as for the number of densification steps, the interval of densification, and these kind of hyperparameters are very arbitrary, and it's very empirical, how we should do that. But basically, we kind of do this step every, I think, 100 or so steps during training.
I mean, maybe my question wasn't that clear, but I was just wondering if the number of Gaussians changes over time. I mean, when you play back the 40 Gaussians.
Oh, no. So the densification only increases the overall number of Gaussians during training, but during playback or during evaluation, validation, the number of Gaussians stays the same.
So basically, you assume that everything is initialized at the beginning, and
yeah,
then some sort of this kind of keyframe can just be consistently used for the later frames.
Yeah, that is actually a major limitation of existing dynamic JS frameworks. That is, we need to assume that everything is in the first frame basically and moves with the scene dynamics. There are some works that actually kind of deal with this issue by kind of modeling the appearance and disappearance of Gaussians in the video, but we don't do that here. I think that's a very promising direction to explore, and I hope that there are more smarter ways to deal with the appearance, disappearance, changing of objects in dynamic scenes in the future.
So maybe bidirectional flow.
Yeah, maybe things like this.
Thanks.
Okay, I think we don't have any time for the next question. But if you want to ask him some other things,
Yeah, feel free to talk to me after.
Thank you very much.
I'm Jinyang Bo from Northwest University of China. Today I'm going to present our recent work about real-time physically based relightening and composition of reading fields with proxy meshes. Reading fields such as nerves and 3D-GS have gained much attention in recent years. Relightening and composition of reading points are important because a complex sense may consist of many different modules, including reading fields and traditional mesh models. And the sense itself can also be represented by mesh models. It is difficult because traditional photorealistic rendering techniques such as path tracing cannot be directly applied to reading field. Our goal is to use reading field as a traditional asset in computer graphics. Current method for relightening and composition of reading point mostly relies on split sum approximation and cannot accurately handle inter-object effects and high-frequency indirect illumination. Previous methods for inserting mesh models into reading fields suffer from low rendering efficiency and simplification in rendering. In this work, we use physically based differentiable rendering to optimize the SVBR DFS and the environmental map of a proxy mesh. And we use differential path tracing to compute the radiance change caused by the change lightning and the incidence radiance fields or mesh models. We borrowed the idea of differential rendering from AR and IMR. In the offline stage, we generate proxy meshes for the radiance fields, including geometry, material, and environmental lighting. At runtime, we compute the radiance change on the proxy meshes introduced by the change lightning and the incident radiance fields or mesh models, and modulated the radiance field by the radiance change. Let me describe our method. This is the overview of our method. In the offline part, we generated the proxy meshes with PBR textures, acceleration structures, and the environmental map through physically based differentiable rendering. In the runtime parts, we compute the outgoing radiance under the new environmental map and the original environment of the incident radiance field to realize it. We use a two-stage inverse rendering pipeline to generate the proxy meshes for radiance field. In the first stage, we use panel-based Gauss splatting reconstruction representation to reconstruct the mesh, and we also use the monocular normal prior provided by stable normal to handle the strong specular reflections and constrain the geometry using a binary cross-entropy loss for the scenes with max. Then we decimated the mesh and generated a texture atlas for it. In the second stage, we use a physically based differentiable rendering Mitsuba 3 to estimate the environmental map and the SVBRDF. We use path replay backpropagation integrator, and the total variation loss is used for regularization the SVBRDF and the environmental map. We use the Vulkan API with the requirement extension to support hardware accelerated ray tracing. The real-time rendering pipeline consists of 3 stages: rendering radiance fields, differential rendering, and the post-processing. We use the original 3D-GS instead of PGSR to represent the radiance field because the novel wave synthetics performance of PGSR is lower than the original 3D-GS, which affects the relightening performance of our method. Since our rendering pipeline is built upon a graphics API, we leverage the graphics pipeline instead of the tire-based software raster to render the 3D-GS. The second stage of differential rendering including 2 passes, G-buffer generation and differential path tracing. We perform hybrid ray tracing on the G-buffer, path tracing with NEE and MIS is deployed to directly sample the environmental map, and the aliens table is built upon for the environmental map to importance sample it. The post-processing stage consists of a denoising path and a composition path. In the denoising path, a cross bilateral filter is applied to denoise the 2 demodulated radiance field computed by differential path tracing. We remodulated the base color after denoising. In the composition path, we blur the 2 radiance maps with a small kernel to suppress the aliasing and then compute the radiance ratio to modulate the radiance field. Let me talk about the experiments and the results. Here are the training details for the second stage of the inverse rendering. We use TensorIR and the synthetic for realized sets to evaluate the relightening performance of our method. The training process takes about 40 minutes for geometry reconstruction and about 10 minutes for SVBR DF estimation. In differential path tracing, 128 samples per pixel are used and the raster roulette is applied. Edge-aware separation denoise with a window size of 9 is applied. To mitigate the inherent ambiguity between the estimated albedo and the lightning, we scale each RGB channel of the base color map by a global scaler according to the ground truth. We report PSNR and SSIM and ellipse metrics and compare them to the inverse rendering baselines based on radiance field. The qualitative comparisons of two datasets demonstrate that our methods can produce realistic relighting results. Compared to the baselines, the specular reflections of our method are more accurate. The quantitative comparisons demonstrate that our method has the best relighting performance in terms of all metrics, while the training time is acceptable. We show the relighting and the composition results in scenes from MIPNERV 360 and Tanks and Temples datasets and the bistro scenes represented by mesh models. The training process takes about 2 hours for geometry reconstruction and 0.5 to 2 hours for material estimation. To achieve real-time performance, we use 2 SPP path tracing with raster roulette, and the sequential temporal denoise with a history length of 20 is applied to reduce the noise. We extract the vase from the garden and the statue from the family as the incident radiance field. We also inserted 2 mesh models, bunny and teapot, into this sense. The resolution of all rendered image is 1920 times 1880. These are the rendering results of the naive completion of our method. Since naive completion does not consider the radiance change of the incident radiance field, and the inter-object effects such as the shadows cast on the scenes and the glossy interreflections, all insert objects seem to be floating in the air, and the appearance of our incident radiance do not match the scenes. Our method makes the radiance field relightable and captures the inter-object effects. This is the video of our out. Okay, this is the time breakdown of our real-time rendering method. We conduct ablation studies on main components of our method to evaluate their influence on relighting performance. We can see that differential rendering can improve the relighting performance compared to only use meshes. And the over-darkening and over-brightening effects occur in different eliminated in full, and the high-frequency aliasing eliminated after blurring. We analyze the impact of triangle counts of proxy meshes on the relighting performance. We can see that extremely low triangle counts lead to poor relighting results. But the improvement is marginal when the triangle count is high enough, and more triangle counts consume more time to render. We also investigate the influence of the sample counts on relighting performance. We can see that the increasing SPP can improve the relighting quality, but the rendering time also increases. Since the improvement from 128 SPP to 256 SPP is marginal, we use 128 SPP in our previous experiments. Let me talk about the future work. We can extend our method to support complex materials such as anisotrophic BRDF, subsurface scattering, and translucency. More accurate inverse rendering method can improve relighting and composition performance. Modeling the incidence radiance of non-distant environmental light source in a more accurate way can be investigated in the future. Animated radiance field models such as HIFFOG can also be integrated into our method. Let me summarize our work. We propose a physically based method to relight and composition radiance field in real time. We first generated proxy meshes with SVBRDFS and an environmental map for the scenes using a differential rendering. Then a unified differential rendering framework using hardware-accelerated ray tracing is performed on the proxy meshes to compute the radiance change introduced by the new lighting condition of the incidence radiance field or mesh models. It should be noted that our method is not limited to relighting and composition of 3D-GS. Although we use 3D-GS as a radiance field in our implementation, the main components of our method are not directly related to 3D-GS. Here are the references of this presentation. Thanks for your attention.
Thank you so much, Hyun, for your presentation. There are some questions? No? I have a couple of questions, more related to the implementation that you did. Can I put in Unity and use in my headset, for example, this kind of thing that you did?
Yes, you can.
So, but I assume that there are some problem about the performance because you use like a GeForce or something like that. If I want to use a standalone headset, there are some parameters that I have to change a little bit to make the performance better, maybe the quality less that you have.
Yes.
Which kind of parameter you need to change?
Which kind of parameter?
It's like sampling per pixel or?
No, we just propose a pipeline, and you can use it as a method to use radiance field in the camera graphics, and
so I can reduce some of them, and I can test in my headset actually.
yes.
Okay, cool. If there's no other question, there's one question here.
I think I didn't get the details, but you are generating the mesh out of these multi-viewpoint images, then use that geometry for relighting. And then, so my question is like, so when you showed the composition stage or the results, I saw some shadows or reflections that appears on the surface of the other part or the environment. Does that mean that you applied your method to the entire environment and also separately to the other objects that are inserted?
No, we just use this for the data sets.
You mean like, so let's say there's a Stanford bunny that you reconstructed with your method, and then if you want to insert to the 360 nerve, MIP nerve data set, do you have to, I'm gonna say, generate the environment from MIP nerve 360 data set with your method, or you can simply use the existing work for that?
Yes.
Okay, so then how did you reproduce the shadows and everything, like the reflections of coming from the Stanford bunny to the environment?
We use the differential rendering method to solve this problem.
Yeah, maybe let's stop that after this session.
Yeah, I think you can take offline this because probably it's more technical, you know. So, okay, thank you very much.
Hello, everyone. My name is Lingyan Ruan. I'm coming from University of Melbourne. And today I'm going to present parameter-free neural lens blur rendering for high fidelity composites. Consistent lens blur rendering is crucial for mixed reality, as it strongly affects the user's sense of realism and immersion. When the real world footage contains lens blur, it's going to be challenging to insert a virtual object. Simply composite them together would break the visual consistency. For example, here, the virtual horse appears naturally sharp and the background is blurred. So the goal of this work is to seamlessly composite virtual object into the real photograph with consistent lens blur, make the virtual object indistinguishable from the real scenes. Okay. To achieve this goal, there are several challenges since lens blur is spatial varying. It varies with factors such as aperture size, focal distance, focal length, even across different cameras. So as we see here, the aperture size reduced and the level of blur reduced as well. As the focus distance changes, the position of blur also changes. Okay, this is the first challenge. And the second challenge is, in our work, we assume the camera metadata and scene steps are unknown. Since in many real cases, this information is not available, it's hard for novice user to handle. But these factors are actually very important for estimate how much blur should appear in the scenes. And the last challenge comes from the scale. Prior works assume that the virtual object and the real world share the same scale, but in practice it's hard to manage. Thus we have the challenge of establishing a clear connection, idea of pixel to pixel correspondence between these two domains to reduce the scale ambiguity. Then our question becomes, how can we ensure consistent lens blur rendering in mixed reality without relying on camera metadata and scene steps? Some previous work have worked on this problem, but they require prior calibration and rely on camera metadata and scene steps, which are not always valuable in the real situation. Other methods try to lift the limitation, but they assume that the real and virtual world are at the same scale, which is not always true, and make the method less robust. And all the methods, they first blur the virtual object and then composite it to the background, which often causes visible artifacts around the boundary. So to address those issues, we propose a novel method consists of 3 components: COC neural network, linear regression model, and a lens blur network. So basically, the COC neural network can estimate the circle of confusion, which reflects the per pixel blur level from a single RGB image, and it limits the need for a camera parameter and scene depth, make the approach more practical and user-friendly. And the linear regression model connects the real and virtual worlds through a per pixel mapping between the COC of the real scenes and the depth of the virtual object. And the lens blur network can handle both lens blur and boundary artifact by fully utilize the network capability. So let me explain in details. So the COC is short for circle of confusion, can be calculated using the scene lens model with parameters such as focal length, focus distance, aperture size, and object distance. Exists method model blur using this equation, but such information is not always available, as we mentioned. So we propose an alternative approach that directly estimates the COC from the single RGB image. We use the object share methods, and this is the corresponding COC map. And the darker region means the COC has a smaller value, which means less blur, and the corresponding region should be sharp. And the brighter region means the COC is larger, which shows the RGB, the scenes will be blurry. Okay, then the goal is to obtain the COC of the virtual object. What we currently have is the COC of the real world and the object depth of the virtual world. However, these two are not in per pixel correspondence. For example, if we want to estimate the COC of the red point on the virtual horse, the corresponding position in the real sense is actually lying behind the horse, as indicated by the purple point. Actually, the right point is indicated as green, because the red point and green are share the same depths. So this motivates us to figure out a shell space, and establish a proper pixel-to-pixel correspondence between these two domains. To achieve this, we found there is a common ground between these two spaces. We simulate the rays emitted from the camera and that hit the virtual object, as well as the perpendicular rays that interact with the ground. By tracing all the points on the virtual object, we can obtain a projected master region that enable per pixel-wise correspondence between the COC of the real world and the depths of the virtual world. And as we mentioned earlier, the COC is derived from the thin lens model and shows a nonlinear relationship between the depths and COC. Since the focal length is much smaller than the thin depths, the relationship can be approximated as a linear between disparity and the COC, where disparity can be regarded as the inverse of the depths, forming a V-shaped curve. When we use the signed COC instead, the relationship becomes monotonic linear. By applying a linear regression model with the shared region, we can obtain the correct COC of the virtual object. So yeah, the right one is the composited COC. It aligns with our expectation, like the horse head appears sharp and the tail is out of focus. And the remaining part is the lens blur network. We use the off-the-shelf lens model that was originally designed to reblur a sharp image using its COC map. But in our work, we take advantage of this network capability, but reformulate the input as a naive composites, which the virtual objects stay sharp and the background is blurred, and change the COC map, which only includes the virtual object. So in this way, the network can inherently handle the boundary issues without introducing artifacts. Here we demonstrate how this procedure works with 3 examples under different focus position, like focus on the front, the middle, and the back. We first obtain the shared space and derive a linear regression model between the COC and of the real image and the depth of the virtual object, and then estimate the COC of the virtual object and apply the lens blur. As shown here, the baguette exhibits a natural lens blur and smooth boundary. This example, this is also another example of the real capture scenes. We are trying to composite a virtual airplane. And we compare our method with the latest work, blind augmentation. And we show our method has a more natural lens blur and clean boundary without artifacts. To quantitatively evaluate our method, we render 3 scenes, and each scene has 9 variants with 3 different focus and 3 different aperture size. And we compare our method with the blind augmentation. As you see here, our method produced more natural blur. Because we use the render scenes, we can see here our method gives the most similar result to the ground truth. And these things, we are trying to insert a virtual board with X inside. And besides the boundary and the lens effect, we can also handle a large bokeh effect. In the other scenarios, we are trying to insert a virtual keyboard. This example is trying to show our method can handle the object experience various level of blur. For example, the middle part of the keyboard is sharp and the ends are blurred. And we compute the PSNR and SSM for the 3 scenarios, and the table shows our method performs much better than existing ones. And to verify the perceptual realism, we conduct a user study. We captured a scene with several billables, where participants were told that there could be multiple virtual balls, or single one, or none. Then we measure the failure rate and calculate the p-value. A high failure rate indicates the user failed to identify the virtual object, demonstrating better perceptual realism. And our method achieved like 90% failure rate. And the p-value was extremely small, show that our method are significantly better than other methods. And our method can easily extend to video. So in this case, we are simulating the airplane taking off. And for these things, we insert a virtual snake. Okay, in conclusion, we propose a new consistent real virtual compositing method under lens blur without sync depth, camera parameter, and our COC disparity formulation bridge the real and virtual domains by a linear relation between disparity and signed COC. And this per pixel correspondence reduces the scale ambiguity between the virtual object scale and the real scene scale. And our method also achieves a high visual fidelity. And our experiment shows that we outperform SOTA method in blur consistency, boundary integration, and user perceived realism. Okay, that's all my presentation. Thank you for your listening.
Thank you. There are some questions? Yep. You have many questions.
Yeah. I'm just excited about this, entire area. So first of all, thank you for citing our papers.
Oh, really?
And then,
which
neural cameras and neural bokeh.
neural camera? Oh, okay.
Yeah, and I have a quick question about the when you insert the object and then try to match the COC map into the scene. Your algorithm is just getting the intersection and getting again into the intersection to the ground, right? Doesn't it mean that you are assuming that the object is inserted in a correct scale?
Not exactly. So basically, finally. Okay, so this process is simulated in Blender rendering actually. So the goal is to obtain the projected master region. So this region, we won't assume they have the scale matching, but instead we derive the linear regression model between these two spaces. Then after we get the linear regression model, any object with arbitrary depth can be calculated according to the linear regression model. So basically, yeah, so we don't assume any scale matching.
Okay, cool idea, thanks.
Thank you.
I think we have one short question, if somebody has. Okay.
As I understand, I mean, you kind of get the value with that perpendicular line. What if the picture is kind of looking down a tall building? Then like the top of the building and then the bottom of the building will have a really different distance from the camera. Will it still work, or how does you handle that kind of case?
I understand your question, but for this process, this is fixed. The camera is fixed. It's must to perpendicular to the virtual object, and the goal is to get the projected master region. So we don't assume any scale or the camera position will be changed in this process. The goal is to get the shell space. Inside this shell space, there is a point-to-point correspondence. Outside the regions, due to the occlusion or due to the occlusion, there is no point-to-point correspondence, such as we saw here. So basically, if you mask out a virtual object in the real photograph, there is no pixel-to-pixel correspondence because the virtual object is not existing in the real photograph, and they assume using the background point, the COC of the background. So the goal is to get the shell space, and the camera should be fixed to get the shell space.
I see. Okay, got it. Thanks.
Thank you.
Okay, thank you very much.
Thank you.
So, good morning, everyone. I'm Katie, and I'm happy to present to you our survey paper, Radiance Field for XR. In this paper, we survey on how radiance fields are envisioned and compare to how they are actually addressed in the current XR research landscape. As you may already learn, radiance field is an important type of new scene representation which can reconstruct realistic 3D scene based on 2D images as input. The two most prominent radiance field representation are neural radiance field, which represent the radiance and light information of the scene as a small neural network, compared to 3D Gaussian splatting, which compress those radiance information into Gaussian point and can be rendered via rasterization pipeline. In this survey, we identify 9 key themes that's relevant to making radiance field in the interactive XR experience. Those 9 key themes, ranging from optimization techniques to scene content editing to finally interactive experience, are increasingly relevant to actual interactive user experience in XR, from the data processing pipeline to the actual model obtaining and training to the actual rendering, and finally to the interactive XR space. In this research, we try to answer 3 key research questions. The first one, as radiance field is a concept coming from computer vision and graphic community, they envision enormous application of this new rendering new scene representation and rendering technique for XR, and we want to know how they are actually envisioned. And secondly, we want to know how they are actually implemented currently in XR research and application. Finally, compared to the envision and implementation, we want to know what are the remaining research gaps for actually adopting those kind of scene representation everywhere in extended reality. So we perform a systematic survey following the PRISMA 2020 guideline, where we collect papers from a wide range community, including XR, HCI, computer vision, graphic, robotics, and multimedia. And from those over 1,000 papers, we select more than 300 papers which are XR mentioned, which means that this contribution include in their paper that they can envision or imagine this technique for to be used in different kind of extended reality application experience. And from those over 300 papers, we have identified 66 XR address papers, which involve either actually in-depth user study, which we label as XR study, in actual extended reality application or experience, or include technical benchmark on headset. Or in those XR address paper, there are actually also XR showcase paper. They are showing proof of concept demo in actual XR setting. From the statistical standpoint, we see that XR are actually addressing all the 9 key themes. However, compared to the ratio of the contribution from vision and graphics and robotic community, the size of XR address are quite sparse at the moment. And also very interesting regarding open source status, there are 2 times more open source in the Envision papers, typically from the vision and graphic community, than the XR address category, which means that we probably need to encourage more open source within the XR community to promote integration and implementation of XR in extended reality. So to go over different key theme in detail, if you couldn't read all the text in detail, you can also scan the QR code above the slide to get access to our project page, and there's also a GitHub repository on all the collected papers. So the first and most important category is interactive experience, which includes all kinds of Radiance Field for XR application ranging for collaboration system, photorealistic agent and avatar that's interactable in VR and XR, and also real-world applications such as medical industry application, and also importantly interaction mechanisms such as physics-based interaction in XR. So here we observe that the most challenge that different work encounter is challenging to track dynamic change in the object, particularly for large static scene in the collaborative system. And also, if you see from the bottom, we also always showed the statistic of XR showcase and versus XR address and open source status. Most work are still remain in the XR showcase stage. So the second part, key theme is user-centric rendering. So this is probably the earliest contribution that the XR community started to contribute for Radiance View to improve the accelerated rendering speed in terms of wide field of view, high resolution, and high frame rate, and stereoscopic rendering on the XR device. And here the most challenge is the aliasing effect that introduced by those algorithms, for example, by those user-centric rendering algorithms leveraging the human visual system. And also most experiments, even though they are in XR address, they actually perform psychophysics experiment. There are still lack of real-world integration of those methods into interactive XR experience to test out different artifacts, additional artifacts that user might experience. And the third category, which is benchmarking and toolkits, where researchers develop a different framework or end-to-end pipeline from capturing to rendering to test the performance or evaluate the different variants of Radiance View. And also there's an increasing amount of user evaluation to benchmark, for example, user perception of Radiance View compared to traditional scene representations such as meshes. And here the most challenge encounter is a standardization of this representation and also their interoperability with traditional game engine, which means that, for example, a neural network model can be hard to integrate into traditional game engine, and there are enormous potential for further discussing standardization of different photorealistic and neural rendering scene representation for extended reality. Coming to a very promising research direction, which is multimodal and multisensory Radiance View, that is currently on the rise, but still sparsely explored area. For example, this means that we want to integrate haptics rendering, textile rendering, or even other kind of sensory modality, including audio, even thermal, or even olfactory modality, along with the photorealistic visual representation. So here the challenge is that traditional, for example, haptics rendering still depends on, developed based on precise geometry, and as a kind of implicit or semi-implicit scene representation, is difficult to make it compatible again with other kind of traditional haptics rendering. And also as the kind of modality grows, it is also research will need to think about unification and synchronization of different sensory and data modality. Regarding content editing, which involve research of editing of the model itself, or adding in the model itself, or editing the scene, they are currently work on object insertion, removal, segmentation, decomposition, and interactive color editing. Here, as introduced by the talks before, relighting and simulating these kind of interesting, intricate lighting effects that can be realistic render with traditional path tracing or ray tracing is still remaining open question. And regarding future opportunities, they are although there are initial integration of Radiance View for interactive editing in XR, there's opportunity to do more diverse and innovative interaction design paradigm, for example, using gesture, hands interaction, eye gaze interaction to edit the scene, which depends again on accurate geometry, which is again a challenging question that's interesting to be investigated on. Going to content generation, which is closely related to content editing, is to bring novel objects or information into the existing scene based on, for example, text to 3D or speech to 3D interaction interface. And here again, the consistency between the general object in terms of light and physics and different material aspect is a challenging research question, and also future opportunity in terms of how to bring such content generation and editing capability into beyond VR environment to immersive mixed reality is a challenge and present enormous potential for research. Regarding spatial registration, which is primarily about inverse post-estimation and camera parameter optimization, here it's important to obtain accurate and efficient registration within a mobile XR device, and so here it presents opportunity to integrate spatial registration tightly with real-time rendering for mobile device. Regarding dynamic capture, the research here, they are actually not, at least from the survey time span, there are no XR address paper yet, and the focus is primarily on human body performance capture or facial interaction capture. And here it is important that as an XR community to research on different perceptual aspects, for example, in terms of social presence, embodiment, and also if user perceive the reconstruct avatar or virtual human as uncanny because due to the highly realistic representation. So finally, regarding optimization technique, so here in terms of the XR Envision, it has the largest amount of paper, but in terms of XR address and XR showcase, the ratio is still kind of small, and it covers diverse topics from resource constraint rendering on mobile device compression, and capturing improvement means that how to guide the author, how to guide the users in correctly capture the scene to improve the accessibility of the technology. So to conclude, in this survey, we identify key research themes of Radiance View research for extended reality, ranging from the beginning of the data capturing and modeling process to the interactive XR experiment. We have seen that currently majority of XR implementation are still in the XR showcase or XR Envision phase, which still you might see a lot of Gaussian spotting or nerve paper, but compared to the number of paper in computer vision graphic community, we are still at the beginning of integrating this technology into interactive XR experience. And also it's important to mention that there are currently limited ethical considerations for such photorealistic scene representation, particularly regarding different intellectual property protection and also users' perception for future research. Thank you very much for your attention. So if you want to have a list of the currents of all the paper we gather, we make a GitHub repository, and we probably add a new paper as the field and the research topic start to grow. And also here's our project page. Thank you very much. Now I can.
Thank you very much. We have just time for one question. Yes?
This was great. Thank you so much for putting all this together. One aspect that I thought was missing and does not get enough representation in the ISMAR community is low power. So to be practical for XR devices, all of these techniques need to also consider power. Yes. So I would encourage that to be included as well.
Yes, that's actually really, really good point, because we try to encapsulate everything in this optimization techniques.
Yeah.
That probably they are not really work in the XR implementation. They are probably work in other community that are yet to be transferred to this domain. Thank you for the feedback.
Okay, thank you very much. Thank you again to all the speakers. The session is closed.